Hi, everyone, and welcome back to the Block 74 Apollo Guidance Computer video series. Today we're on part 17, and we're going to start talking about the G register. Um, so if we look at the G register and kind of where it sits in the overall architecture, is the G register is really our memory buffer. So it basically connects to our memory, both fixed and erasable, and passes data between that memory. So in that essence, it's actually quite simple. It'll take data in, take data out, um, and based on the contents of address register S, it'll determine whether it's bringing in data from fixed memory or erasable memory. And in the case of erasable memory, it can write the contents of that to the erasable memory. Now, what makes it a little bit more interesting, like most registers, they have more than one function, is they have this little function called editing control. And this allows various shift operations to be performed on data going into the G register. So we'll talk about that in the next episode because that starts getting a little bit more complicated. But today we'll cover kind of the basics of the G register, at least in its function as a memory buffer. So it's a 16-bit. I'll move myself over here so I'm not blocking the text. It's a 16-bit register, which is a little bit odd because as a memory buffer, because of the parity bit, only 15 bits are used in the memory itself. However, because the G register is used for a few of these other things like shift operations, and we'll talk about this L2GD um, control pulse, it actually is a 16-bit register. And we'll talk about parity in a subsequent episode because we are going to hook that up so that we can actually generate parity alarms, which is an important part of how the AGC functions. Now, if we look at the control pulses that kind of feed into the G service, if you will. Of course, we've got our write timer. We have WG, which is our G register write enable. But this also provides our inputs to editing control. So you can see kind of the description here. So normally the WG, clears register G, writes the contents of the write lines 16 through 1 into position 16 through 1. So that in of itself, fairly simple. Except if the S register contains addresses octal 0020 through 0023, in which case it will execute one of it basically won't load the data in directly into the G register. It'll either cycle write. So cycle write is a shift write with wraparound. So the bit gets pushed off one end and comes back the other end. There's just a regular shift write, which drops the bit that gets pushed off the end. There's a cycle left, which is basically the opposite of cycle right. And there's EDOP, which is shift left 7 bits. So based on what memory or what the memory address is set to, it will perform one of these functions. And like I said, we'll talk about those functions in the next episode. Um, in addition to WG, there's this L2GD control pulse, which copies the contents of the L register to G, but it's not a one-to-one copy. It actually, you can see, kind of shifts things over by 1 bit, except for the parity bit, the L15, which gets booted, and inserts this MCRO, the contents of MCRO into position 1. So MCRO is a control pulse that's generated during multiply instructions. So that's one of the other functions that the G register is used for. And then, of course, we have a RG to actually read contents of the G register out onto the write bus. So, like I said, in of itself, it seems like a pretty normal register, except for this editing control. But then you also have to factor in that it can also read data out of the write or out of the memory and write data into the erasable memory. So when we think of that, that's where some of these timing still comes into play that we talked about with our S register and memory timing. So when it comes to erasable, um, we need to be able to pull. So when we're reading data out of erasable memory, we need to basically be able to bring that data into the G register. And then we also have to be able to write into it. So the write actually that one's fairly straightforward. Read gets a little bit more interesting because we got to, with the timing, not only are there potential to read data out of erasable memory and fixed memory, but we can also be reading contents of the write bus or the L register, depending on basically what's happening. So the kind of where we start loading data in from memory is something we'll cover in the next episode, but we will be able to talk a little bit about the write in this episode. Okay, let's go and take a quick look at the design. So I'll just bring up my G register. And by and large, so this part over here is pretty standard compared to the other registers we've talked about. So we've got 474LS173. So these are 4-bit registers. This gives us our 16 bits in total. We've got our LEDs so we can see what the contents are. And then to write out back onto the write lines, we have these a pair of LS74248 octal transceivers. The control kind of circuit or logic for these two are pretty, again, straightforward compared to what we've seen before. So we've got our general reset that's buffered, of course, so we can reset the contents of our registers. We have our write timer, which is also buffered, that we can use to clock data in. We can write data in through, at least through control pulses, through either one of these two signals. And then we can also write data in from memory. So if we're doing basically reading memory, we'll have to basically pull data from memory. So like I said, we'll talk about that in the next episode. And then we've got the read, so where we basically push content out onto the write lines. That's just a simple RT NORD with RG. So it's our read timer combined with our read control pulse. If I just look at our little simulator here, we can see for our write, if this is set to 0, then we go low here, which is because it's negative logic. That's exactly what we want. If we go 0 here, again, it goes here. So this kind of, again, controls how we can read or write data into the register from the various write lines. So either the L register or write lines. We'll have to add some additional logic to write data in from memory. But like I said, that we'll cover that in the next episode. And then we've got our read also. If RG is enabled, so again, low control logic, and we pulse our write timer, we'll pulse the clock to be able to push the contents of our octal transceiver out onto the bus. So that part, again, fairly straightforward and fairly similar to previous registers that we've covered. Now, the data that comes into the G register is, again, a little bit different. So we have a couple of options. So we have one here, so that we're basically using a couple of 4-bit or basically quad 2-to-1 selectors here. So we've got one set here where if we go 0, which is basically tied, you can see all back here, to our L2DG control pulse. So if that's asserted and that it goes low, we'll basically pull the selector low, and we will load in the contents of the L register based on that pattern that we saw within the PowerPoint. If not, then we'll actually go to this selector, and this is where we'll either pull in the contents of the write lines. We can see here, write line all the way down. And then right now we've got, these are just hanging because we still working on designing that editing logic, as well as where we will bring in contents of memory when we want to just load it from memory. And I haven't quite decided if I will do that here, or at least for the memory, do that here, or if I will just bring it in directly into the registers based on timing. So using the clock signals and the timing signals to determine exactly when we can write those in and basically ignore what's coming in off of these selectors. So that's still to come. The other contents we'll bring in basically if we're either have those three addresses. So, or sorry, four addresses: 0020, 0021, 0022, and 0023. So I've created a little bit of logic here to basically select whether we have those memory addresses in our S register. So I've got a combination here, and this is a control signal that I created that I'll show you just in a second. I call it S high 0. We've got the contents of S03 and the contents of S04. Because if you look at basically the octal representation of those memory addresses, so anything that's in 0020 is actually bit 5 of the S register goes high, right? So if it's high and everything higher, so basically bits 12, 11, 10, 9, 8, 7, and 6 are 0, and bit 5 is high, you're in the 20s, right? So we'll just need the first 4 bits of that. Now, the reason I'm not kind of putting all the logic to kind of combine, okay, well, we need S030 and we need S040. That's why we invert them so they become 1s, and then we put them in our AND gate. There are a couple of other instructions or sub-instructions within the Apollo guidance computer that is dependent on the address of the S register containing certain values. So there's I believe it's called the WOVR command, WOVR, that looks at the contents of additional memory addresses in S, and depending on what it contains, it'll perform different functions. So I did go back and add just a little bit of additional electronics to the S register, and this is where I'm just going to take look at the contents of S12, 11, 10, 9, 8, 7, and 6. Make sure that they're all 0, and if they are, I'll generate this little S high control signal. And like I said, I'll use that not only in the logic for the G register, where it's needed to determine if we're doing a editing control instruction, or some of the other, like I said, the WOVR, which also looks at similar addresses and performs interrupts or timer increments. We'll probably end up having to do a little bit more of this because there are some other areas in memory, kind of low memory, that are used for counters. And so there's a variety of kind of increment instructions that are used to manage those counter controls. So this may change as I start getting into understanding the kind of the logic and controls around the counters within the Apollo guidance computer. Just again pop back over to our simulator here, and we can see kind of how we've got basically how this logic works. So if any of these contain a 1, we'll of course this will drop low, but if everything is contained as 0, we'll go high, and we'll use that to determine whether we're with this, when combined with both S3 and S4 being 0, that will be our determination whether we're running a editing control instruction. And from there, we'll be able to start doing our shifting back and forth. So the first 3 are actually fairly straightforward. You can use a shift register to just shift 1 bit left or shift 1 bit right. And then whether you carry around or not is kind of dependent on whether you're doing a cycle command or the shift command. That last one, that EDOP, is a little bit more interesting. So I'm still working how I want to execute that, because you have to do multiple. If you use a shift register, you have to do multiple shifts. So you'd have to get multiple control pulses, or sorry, multiple clock pulses within a single clock pulse, if you will, in order to, just shift the number of bits across. So like I said, I'm looking through a couple different options as to how I'm going to implement that. Anyway, I think we'll pause here, stop for today, just as I said, before we get too much into the editing logic or the memory timing and how we write memory or into the the G registers and basically retrieving it from either fixed or erasable memory. I will be out of town next weekend, so unfortunately I won't be able to record next weekend, but I will be back in 2 weeks and we'll start talking about editing logic. So again, thanks for joining. As always, if you want to follow along with what I'm doing, click subscribe so you'll know when another video comes out. I do try to record about every week. And generally, I've been fairly consistent with missing the odd weekend here or there. And any comments, questions, pointing out mistakes or errors that I've made, please don't be shy. Always looking to interact with folks that are following. Have a great week, and we'll be back soon. Thank you.